We usually map human history through the lens of political ideologies, the decisions of great leaders, or sudden technological sparks. But the energy researcher Vaclav Smil uses a different framework. He strips away the politics to look at the mathematical reality underneath. Energy is the only universal currency. Regardless of a society's culture, language, or era, any civilizational achievement requires a baseline thermodynamic transaction. To understand how we scaled from biologically constrained hunter-gatherers to a globally interconnected terawatt civilization, we have to map our history against strict physical limits. Every historical milestone we recognize is, at its core, an upgrade to our energy conversion architecture. The first physical constraint governing all human expansion is the first law of thermodynamics. Energy is conserved. It is never lost. But the act of converting that energy for human use degrades its quality. This introduces the second physical constraint, the second law of thermodynamics. This one-way loss of useful work is known as entropy. Human civilization requires a massive, continuous influx of highly organized, low-entropy energy sources, like biomass and carbon fuels, to build and maintain order. The combustion and metabolism of these low-entropy sources inevitably produces high-entropy dissipation. We see this as waste, emissions, and ambient heat. Human history is a perpetual, precarious feedback loop, balancing our immense energy consumption against the inevitable accumulation of entropy. Our first major energy revolution was biological, predating any tool or machine. The transition to bipedalism. Standing upright was a high-risk energy strategy. Sacrificing pelvic width increased birth mortality, but it offered an immediate thermodynamic advantage. It drastically reduced the surface area exposed to downward solar radiation. This superior heat dissipation allowed early humans to occupy hotter hunting environments during the day, and it freed our upper limbs to carry weapons and harvest higher-density food. This richer diet provided the massive energy surplus required to fund our most expensive biological organ. The human brain consumes 3 times the energy of a chimpanzee's brain. This intense caloric investment yielded language, social complexity, and tool use, separating human survival strategies from all other mammals. The human brain was our species' first structural energy deficit, forcing humanity into a permanent cycle of seeking ever greater energy surpluses. Agriculture functioned as a large-scale landscape engineering project, designed to maximize the yield of digestible energy to support high population densities. Expanding these complex agricultural systems required massive labor pools, but human muscle power has a strict physical limit. Societies began harnessing prime movers, external forces deployed to multiply physical work. This started with draft animals. Across the globe, non-living prime movers were deployed next. Water and wind power were harnessed to process grain and manage water systems. Some societies reached a thermodynamic plateau. Han Dynasty China achieved massive early innovations, including cast iron plows and complex seed drills, but their energy infrastructure eventually stagnated. Medieval Europe avoided this plateau by aggressively scaling their dependency on water and wind. They built highly concentrated power centers, utilizing 5-kilowatt water wheels capable of doing the work of 60 men. This chart plots wheat planting efficiency over time. In the 18th century, it required 200 hours of human labor to plant a single hectare of wheat. As prime mover deployment scaled, we see an aggressive drop in required labor.
By the early 1900s, highly mechanized California models required less than 9 hours per hectare. Pre-industrial societies advanced because they engineered mechanical architectures that multiplied energy capture far beyond the biological limits of the human body. The Great Transition was the pivotal shift away from living biological drivers and biomass fuels, moving society toward the mass combustion of fossil fuels. The steam engine served as the primary physical bridge into this era. It was the first practical device to successfully convert dense, fossilized chemical energy into continuous, reliable mechanical work. This broke a thousands-of-years-old dependency on immediate solar radiation, which had dictated wind, water, and crop cycles. This chart visualizes the resulting explosion in physical power. Between the 1800s and 1900s, coal extraction rose 100 times over, and oil production multiplied by 300. Across the 20th century, total global fossil energy extraction grew 14 times. Accessing low-entropy carbon stores provided a density of raw power that permanently altered the speed of human material progress. Geopolitical dominance during the modern era was largely dictated by which nations achieved higher net energy returns from their resources. The centers of global power shifted alongside prime fuel sources, from the Dutch reliance on peat to the British Empire's mastery of coal, to the American ascent via hydrocarbons. This influx of dense energy had an instantaneous impact on individual living standards. In 1954, nearly 60% of French homes lacked basic plumbing. By 1990, ownership of indoor appliances and central heating was almost universal. A citizen living in the year 1800 experienced a material reality far closer to the year 1300 than they did to the year 1900. Global supremacy and modern comfort are the direct thermodynamic byproducts of successfully controlling massive energy flows. By the late 20th century, we operated under a single assumption: continuously increasing energy inputs would guarantee a continually improving society. This scatterplot maps per capita energy consumption against quality of life metrics, revealing a phase of diminishing returns where high consumption fails to correlate with well-being. Despite the highest per capita energy burn, the United States ranks 31st globally in infant mortality, alongside mediocre reading scores. This is the entropy bill coming due. It is the physical and societal waste generated by a system operating at maximum thermodynamic throughput. We see the physical manifestations in vast food surpluses, leading to obesity epidemics, and fossil fuel combustion vastly outpacing the biosphere's capacity to absorb emissions. Pumping more raw power into our current civilizational architecture only exponentially increases its structural waste. The current techno-optimist narrative relies on the belief that discovering a limitless, clean energy source, like nuclear fusion, will solve humanity's physical constraints. But if the underlying civilizational architecture remains unchanged, this vision fails the laws of physics. Feeding infinite energy into a structurally inefficient, high-waste society simply generates infinite entropy, which will inevitably overwhelm the system's boundaries. Vaclav Smil's ultimate warning is clear. The defining challenge of our era is no longer the historical struggle to extract energy from the Earth. Our new evolutionary hurdle is mastering the complex control of how that energy dissipates. If human civilization cannot successfully manage the feedback loop between energy flow and entropy, mathematics dictate our highly ordered society will collapse into disorder.